Today we're going to look at how to create a custom concurrent program using the WorkQ programming model. So what we're going to do is create a relatively small application that expresses the logical structure of a highly concurrent workload. Now this application is going to be built in conjunction with the WorkQ standard library, which is going to handle much of the difficult parts of distributing an application. Now, your application is going to contain the logical structure, and you can write this in most any programming language like C or Python or Perl. And the job of this program is to define independent tasks that can go out and run in a distributed system. For each task that's created, we're going to submit that task to the WorkQ library. And a typical WorkQ application has a very large number of tasks, measured in thousands or perhaps even millions. After that application has submitted its first round of tasks, it will tell the WorkQ library that that's it for the moment by invoking a function called wait. And wait simply means I'm done for now. You go do some work, and I'll wait for you to be done. So this programming model is sometimes known as a submit-wait programming model. Now, after some time, the library is going to go out and do its work, and then go back to the application and say, OK, here's a task that's done. And then the application can take that result, perhaps compute something locally, and then it may submit some more tasks in response. And then it can keep going until it decides that it's done. Now, the interesting question is what happens between this wait and done. And this is where the WorkQ library is going to do a bunch of work for you. So as each of these tasks is given to the WorkQ library, it goes into an internal queue that's kept in memory. So let's suppose here that the queue has tasks 1 and task 2 and task 3, perhaps a large number of them. Now, the way we define a task here is that it consists of a command line to be executed, along with the files that are needed as inputs, and the files that we expect to be produced as outputs. So each of these tasks implicitly depends on some files that are in the local file system. So I'll mark them down here so we don't forget about them. Now, nothing's going to happen until we have a worker that's ready to run some tasks for us. So what we can do, at least to begin with, is we can start a single worker by hand. And that's really easy to do. All I have to do is type the command WorkQ worker. And then give it the name of the master to talk to. So if I start a single worker, that process is going to wake up. And the first thing it's going to do is set up a cache directory for commonly used files. And then it's going to go it's going to connect to the master to say, here I am, I'm ready to do some work now. Now, the WorkQ library is going to see that there's a worker available and it has some tasks to run. And so what it's going to do is it's going to send over a task along with the files that it needs. So let's suppose that task 1 needs file A. So file A is going to get sent over. It's going to get put into the cache. And now we're ready to run task 1. So the worker is going to create a separate space for that task to run. And this is generally known as a sandbox. But it's really just a directory that provides a local namespace for that task to run in. We'll call this sandbox T1 just because it refers to task 1. Now, each of the files that's needed as an input is going to get linked into the namespace of that sandbox. So here's A. And now we're ready to run task 1. So the worker is going to run task 1. That may take a while, but eventually it's going to produce an output, which we suppose is B. Now, once the task produces its output and it's done, the worker is going to send a message back to the master that says, okay, this task is done. And then the WorkQ library has an opportunity to go and get the output files. And in this case, it's file B. And so B will be written to the local file system here. Now, if B might be used by a later task as an input, then we can keep it around. So if the task identified this as cacheable, then the worker will take B, put it back in the cache. And when we're all done, it will delete the sandbox directory. So there should be no evidence left of that task on the machine. Now, this sandbox is very important. It gives each task a private namespace in which to work. And what that does is it guarantees is that no matter where that task runs, it's only going to see the files that it's supposed to see. So if you end up running on different machines with different properties, you shouldn't have to worry about all those differences because the sandbox is going to be the same in either case. Now here I've shown one task running at a time, but actually what's a relatively common case is that the worker might be managing a large number of cores in memory. So let's suppose, for the sake of argument, that this worker is managing 4 cores and 16 gigabytes of memory. The worker is capable of running multiple tasks as long as they fit in the resources that that worker is managing. So let's suppose that this task needs 2 cores and 8 gigabytes of RAM. How do we know that? Well, the application would have had to say that from the beginning. Here's a task and here are the resources that it needs. If that's the case, then there's some space left over. Then the WorkQ library knows enough to call up the worker and say, you know what? Let's run 2 tasks at a time. So here's task 2. And what's kind of handy is that if this task needs the same input file as task 1, then the same input file will be linked in, and we'll really only have 1 copy of the file instead of keeping around multiple copies. So here, task 2 produces file C, and then when that's done, that's going to get transferred back to the master. And when the task is all done, it goes away. Now, this is known as a master worker programming model. This whole piece over here, consisting of the application and the library, is generally known as a master. So a master worker programming model. Now, I've drawn a picture here that has only 1 worker, but really the point here is to do very high concurrency. So in practice, we really want a large number of workers running. So imagine having 1,000 different workers running. And the way you get those workers is to use the WorkQ factory to submit a large number to a batch system. So that is the master worker programming model using the WorkQ software.